Hello?
Hi, how are you?
All right, how are you?
I'm good.
Good. Hi. So, welcome to the meeting. Again, had two meetings this week. We had DevoWorm and we had our open source meeting. So, open source meeting, I talked a little bit about our activities at BICA, which is the Biologically Inspired Cognitive Architectures Conference I talked about last week in this meeting. So, I ended up doing an overview of that, of our activities of it. So if you want to, and actually I cut that part out of the video. So one of the things I've been doing on our YouTube channel is I've been taking out clips of different features from different meetings and putting them as smaller videos. So you'll find that on the YouTube channel as well. So that's a recap from this week. Why don't we get started? All right, so our Slack, I have a couple of articles that were put in the Slack from this week I wanted to cover. The first one is this one, and this is about games like chess, or I guess chess in particular, and machine learning. And the reason I found this interesting, well, first of all, because it's an interesting topic with respect to what we talked about in this meeting. But the other thing is that Hussein Ather, who's one of the lab members who comes to these meetings and also to DevoWorm, made a comment in one of the Devo, I think it was this last week, where he said he doesn't think chess is a good metric for intelligence. That's his personal take. And so I think a lot of people have a similar take. Certainly chess was important in the GoFi era of AI, where they were building symbolic machines and they were getting to play chess and other games like that. But this is also, just kind of his idea that we kind of associate chess with intelligence, and he doesn't think it's a very good metric. So this is kind of going over this article. He responded with positive interest in our Slack, and so let's get into this paper or this article. So this is all our games turn into Calvinball. Why lessons from chess don't apply to machine learning. Okay, so this is Ben Recht. This person runs a blog where this source material is from. I want to first pick on some peculiarities of this essay, and then turn to why I think Sutton, which is Rich Sutton, who is an expert in games but not pattern recognition, misunderstood the transformations that occurred in supervised learning in the 2010s. And then in subsequent posts to this, the author turns to their own bitter lessons from the 2010s. This was, of course, during the rise of deep learning. Okay, so one thing that always bothered the author about Sutton's examples is that they conflated parlor games and pattern recognition. So Rich Sutton wrote this article called The Bitter Lesson, which we've talked about extensively in this group. And, he goes through kind of what the bitter lesson is and all that. And Sutton, of course, is one of the originators of reinforcement learning as a source of artificial intelligence, as a source of simulation. And Sutton is reflecting on why we can't achieve, lifelike levels of AI, I guess. And so he kind of talks about games and pattern recognition as sort of a similar problem type. And in this article, the author basically distinguishes between the two and says that they're very different problem domains. Both board games and pattern recognition are fundamentally two completely different problems. And their computational solutions were also quite different, even though both use neural networks as part of the solution. chess and Go are both perfect information games. They have clear, unambiguous rules and clear definitions of what a win, loss, or a draw mean. So, there's a little bit of background on this. When they say perfect information, this is a term from game theory that refers to how much information are you assuming each player has in the game. So if I have perfect information, I have or can acquire all the information I need to solve the problem. So if we think about chess, we have a chessboard, we have pieces, and you can play the game to its conclusion to see if there's a winner or a loser, or if there's a draw. And I can state that unambiguously in steps. So there are a certain number of moves that I can make to get to one of those outcomes. Furthermore, if I have enough information about subsequent moves, or if I can get enough information about predicting possible moves down the road of my opponent, I can basically predict their gameplay and I can respond in kind. So it's perfect information in that you have all the information you need to play against your adversary or to build a simulation that you can reverse engineer. You can describe all the moves that go into this. And so that's true of chess, but not necessarily true of pattern recognition. So if I have a pattern that I recognize, maybe I can't describe all the steps to that pattern, how the algorithm, say, arrived at that pattern. And I certainly can't replicate it again and again. Sometimes a pattern will have different ways of getting there. So I think that's kind of an interesting point, that that's a distinction between something like chess and something like pattern recognition. And there are other things we can think of as well that produce some sort of coherent output, things like building a swarm. We talked about swarm, collective behavior, swarm intelligence, things like that. And that's kind of a similar thing. And maybe it's more on the side of pattern recognition, but it's actually probably its own thing. So again, chess and Go and there are other games in this category have clear, unambiguous rules and clear definitions of different end states. Now, John von Neumann and Oscar Morgenstern wrote a book on games and intelligence, and this is kind of the founding book of game theory. And I didn't pull that book, a digital book, out for this, but it's an interesting data to read. And so, of course, von Neumann invented the von Neumann architecture, and from that kind of led to this interest in games, and then applying games to computers, and that's kind of how we got our chess benchmark for intelligence. It's through that sort of interest in synergy. So in their book, von Neumann and Morgenstern went so far as to call chess trivial because there's definitely a deterministic algorithm that solves the game. So you can use a deterministic algorithm because you have perfect information in these games. You could either write a code book to predict the optimal next move, or you could enumerate a game tree down to 40 moves and backtrack an optimal move. So in chess and other games, you can build a tree. That tree describes the entire game. And as long as you have enough computational power to look ahead, maybe 4 or 5 steps or maybe 6 steps, then you can actually figure out how to outplay your opponent. So in that sense, it's deterministic. There is undoubtedly an algorithm, the one of unfathomable complexity that solves chess. So as long as you have enough capacity to represent all this complexity that you need, you can solve chess essentially. Building a computer program to approximately solve chess is, of course, a daunting engineering challenge. Claude Shannon proposed an algorithm that would beat chess players in the 1950s. before we even had computers, personal computers, I guess, to attempt approximations. Shannon proposed performing a truncated tree search with a reasonable function at the node to evaluate the quality of a board position. It would take decades for computers to be fast enough for Shannon's methods to play competitive chess. But of course, eventually, Deep Blue was able to beat Garry Kasparov in 1997. And Shannon's algorithm that he proposed back in 1950 would form the basis for the strategy that Deep Blue used to beat Garry Kasparov. But, however, the approach that Shannon proposed and was implemented in Deep Blue is only a bitter lesson if you are committed to the NeuroSim program of using chess to understand human expertise. So Newell and Simon, of course, wrote another book in around 1970 where they kind of furthered this chess metaphor and started to apply it to looking at expertise and looking at decision making and things like that. So again, we're using the chess metaphor, we're using the same model, the same deterministic model, and the idea is if only you can build a decision tree in an organization or for an individual, and only if you had enough information about the number of moves you need to look ahead, you can actually solve all sorts of problems. And that may or may not be true. We know from subsequent research to when they were doing their research that decision making is maybe not deterministic. Maybe that's not a good way to describe it. We often use heuristics, and it's maybe not the best way to represent what they were trying to do. People do not play chess the way computers do, but the idea that a computer with enough power could beat a human was known in the 1940s. Though the algorithms were a bit more complicated, and the computing hardware a few generations later was much more powerful, the solution to Go was not a huge leap from this basic strategy of tree search and heuristic board evaluation. So it's basically where you can represent all possible strategies of the tree and then search the best solution given your opponent's moves. And you can use that in chess, and you can use that in Go, and you can use that in other games. But when you get to something like pattern recognition, it's unsuitable. Pattern recognition, on the other hand, is fundamentally a problem of induction. So this is where we're moving now to pattern recognition. And again, we're trying to find patterns in data or patterns in some sort of maybe some real world image. And we're trying to figure out if these patterns maybe mean anything. We match them with maybe like a training set and we look and see what those patterns are. So sometimes we find patterns we weren't expecting. Sometimes we find spurious patterns. Sometimes we find well-supported patterns. And so what is the goal of pattern recognition? So if we ask the question like that, we see that pattern recognition doesn't have the same goals as chess or as Go or any of these other games. I give you a sequence of examples and ask you to infer a property of the next element of the sequence. So again, this is like a large language model where we have a vocabulary and we have to infer what element comes next in a sequence. Or if we have a visual pattern recognition problem, we have to figure out what's the most likely state for the next pixel. These are not the same as the kind of tree search that you would use for a game like chess. It's a different type of representation. There is not and cannot be a codebook that mathematically provably solves this problem. We have known this for 300 years. Unlike in chess, there cannot be a mathematical proof that a pattern recognition system works. So we can't really build a proof to show how a pattern recognition system works and have it be mathematically provable. Because, for one thing, we don't have perfect information about the pattern. Like if we have a large language model, we have a vocabulary. We know what word is most likely to come next. But we can't say that, language in that sense isn't deterministic. There are a lot of similar sentences, there are a lot of similar statements, and putting it together is not a matter of looking it up in a table or a code book. You have to have this sort of probabilistic model, and you have to have verification from the real world and things like that. So I don't think I fully appreciated the point until recently. So let me not pick on Sutton for not realizing it in 2019. This is when he came up with the bitter lesson, and it kicked off this whole round of discussions about what can and can't be learned by machines. How pattern recognition differs from perfect information games helps illustrate why the current landscape of machine learning engineering design is frustratingly convoluted. So that's kind of the take here on the difference between chess and pattern recognition. Now, if we go back to Sutton, Sutton had some things to say about computer vision. And so the things he had to say about computer vision, so he says, early methods conceived of vision as searching for edges or generalized shapes or in terms of SIFT features. But today all this is discarded. Modern deep learning neural networks use only the notions of convolution and certain kinds of invariances and perform much better. So, methods of pre-deep learning methods of computer vision involve trying to find these features in, like, say, an image where you have these, these motifs, and then you had to match them with templates, and work to some extent. But of course, deep learning kind of got around a lot of that by being able to do this through sort of a different strategy. So SIFT was from 1999. I know this is ancient history now, but I would not call it early computer vision. SIFT features were invented after convolutional neural networks, and the two coexisted for different purposes in the computer vision community. Jan LeCun, no fan of shallow learning methods, would always sing the praises of SIFT, notably because SIFT had been rejected 3 times by illustrious computer vision conferences. So what he's saying here is that the things that Sutton was talking about with respect to computer vision was he was creating this artificial dichotomy between sort of these methods that weren't deep learning and deep learning, and how that works much better. But of course, there are methods that came post-deep learning or came at about the same time. So the components of deep learning, like convolutional neural networks, came before things like SIFT. Having looked at SIFT features myself, I'm not sure I'd say that they leverage human knowledge of the domain more than convolutional neural networks do. As Jan LeCun also liked to point out, SIFT features are a convolutional neural network, just one where David Low crudely hand-coded the weights. So this is where, you have basically a convergence to the same type of method, but using different ways of doing it. It's not worth kind of making up this false dichotomy to sort of make up a story about why something worked and why something didn't. If you look at the lowest layers of a convolutional neural net, you will always see simple SIFT-like edge detectors. So, moreover, if you want to solve pattern recognition, it isn't sufficient to merely output SIFT features. You have to apply some sort of classification function to them, be it linear or nonlinear. Nonlinear classification on SIFT features leverages computational power in the sense that if you have enough data, its error rates decrease. So this is an interesting point, because we said about solving chess that chess is a deterministic game. You have perfect information, and you just need to have a tree of large enough size, and if you can represent that in a computer, then you can quote-unquote solve chess. Now, in the case of convolutional networks and SIFT and all of this, we want to do nonlinear classification, we basically have to have enough data to not necessarily solve the problem, but to decrease the error. So it's a sort of probabilistic version of what is a deterministic problem in chess. But of course, you need to have both rely on having a lot of computational power available. But you can clearly see that there's sort of the same trend that computational power gives you an edge in both cases, but it's a different type of thing that is happening. So back to the article. However, convolutional neural networks undoubtedly outperformed SIFT-based methods in the 2012 ImageNet competition, and people immediately saw how to scale AlexNet, where it was not clear how to move beyond the second place SIFT-based entry. Now, Sutton is vaguely alluding to SIFT as using more human knowledge than convolutional nets, and that this hindered progress. So we should learn a lesson. So let's try to apply it. A multi-layer perceptron with one hidden layer, a convolutional neural network, and a transformer all leverage computation and don't leverage their human knowledge domain. Why do we use transformers instead of MLPs or ConvNets? Okay, so that's kind of one part of this updated bidder lesson, I guess. Now, the original bidder lesson by Sutton has nothing to say, but the answer is clear. It's because transformers seem to work better on evaluations people care about at the scale of data they care about. Is that a fully rigorous statement? No. Are the rules of evaluation as cut and dried as they are in parlor games? Also no. If pattern recognition is a game, it's one of Calvinball. So Calvinball is this game that, if you remember the comic strip Calvin and Hobbes, Calvin used to play this game where he'd constantly change the rules. And so you could never win because the rules were always changing in Calvin's favor. And so this is kind of the idea that you can shift the goalposts or shift the rules of the game and, kind of come up with a story about why things work. And so this is kind of the thing about pattern recognition, if you think about pattern recognition as a game. Okay. But what unites parlor games and pattern recognition is evaluation by competitive testing. Whatever seems to work best today in a particular leaderboard is what people run with tomorrow. It is undeniable that competitive testing has been the primary driver of the academic and industrial branches of machine learning, which has consumed the rest of artificial intelligence. That said, I worry we have lost something in the embrace of pure scaling through this sort of Calvinball. This design pattern can't tell us what to do after we hit the inevitable wall of diminishing returns. Okay. Yeah, so this is great. And then, so that's this article. And I thought it was really interesting because we did have this discussion about chess, about intelligence. And then, of course, there's this issue of chess being sort of a thing that defines artificial intelligence pre-deep learning. And now with deep learning and post-deep learning, we don't really have the go-to of chess anymore as a metaphor. We really kind of lean on pattern recognition. It's important to realize that these are two separate types of things. Okay. The next article I want to go through here, this is from Diagram Monkey blog. And again, I just ran across this blog. It's I don't remember who the author is, but this is where this is from. And this is an article on meta science or open science. And there's been this sort of argument in meta science about sort of the utility of significance testing and how to reform science. So the idea is that a lot of scientific results have been based on significance testing, and a lot of people think that significance testing is flawed, and that can sometimes call a lot of scientific results into question, there is also this issue in parallel to that of the change of practice in science. So, how do you best approach changing practice? Do you kind of shame people into changing practice? Do you incentivize people into changing practice? Or do you try to come up with good alternatives to convince people to change their practice? And so this blog post hits on a lot of these issues. So the title of this is Metathugs, and I know this is pretty in your face, but that when I say Metathugs, they're referring to metascience and some sort of the maybe unsavory practices within that field. Okay. And this is independent of like science reform, by the way. This is actually getting to science reform. So just so we're clear what metascience is, it's the science of science, or it's the science of studying scientific methodology. So there's this two-part series on how to science a science with science, which is like some reflections on metascience. Metathugs is one, and there's another one I'm not going to talk about. And so, yeah. So I knew things had definitely gone wrong when science invited us to meet the data thugs. So this was an article that was published in Science Journal, and it was about sort of how people go and they look at data sets that have been published, or look at papers that have been published, and try to interrogate the data to make sure that there's no fraud, or there's no sort of mistakes in the data or things like that. There's a whole cottage industry of people who investigate papers that have already been published, and if they suspect that there's some malfeasance or there's some degree of error in the results, they will go through and reanalyze the data and see if they can replicate the paper or find the errors in the paper. And maybe this people's shock, or maybe to no one's surprise, there are a lot of papers that are maybe missing the mark in that way. Sometimes they have to be retracted, and sometimes it's just a matter of that these things weren't caught in peer review. And we've talked about this before. So this is it was an article on Science Journal, and it's called Meet the Data Thugs, and it's kind of a provocative title for an article. It was basically about these meta scientists. Not only were they thugs, but they were enforcers, watchdogs, whistleblowers, sleuths, etc. So basically, these negative connotations to an activity that is, probably necessary, and a lot of, one could say that if you're a large, high-stakes journal, you maybe don't want people poking around in some of the things that you've accepted, because it can hurt your reputation. But in any case, and again, if you're like a scientist, you might feel threatened by people poking around your work and making the assumption that it needs to be investigated with a critical eye. I mean, that just happens as a matter of protecting your territory. So, of course, thug is not a positive word, and I was surprised that someone would choose to describe themselves in that way. Nevertheless, the article is positive and generally supportive of thuggishness in this sense. What the thugs were doing was investigating published papers, checking the math, demanding data, prodding suspect analyses, tutting, which is kind of, being self-righteous, that kind of thing. The title of the piece had them out to expose shoddy and questionable research. Okay. So it's like, some of this is self-description, some of this is sort of a lot of times in the glamour journals, you get this sort of salesmanship of something. You have to you frame it in a controversial way and you get discussion. So that's kind of where we are with that. And so I suppose that this is a good thing. So, it's not a bad thing to try to do this and to try to hold people accountable. But there is this aspect of kind of almost, kind of a revenge-driven thing. But overall, this is a good thing. This is a thing we need to have. We need to have these checks in the scientific community. We're dealing with scientists, after all, and they were operating the error-correcting mechanism as supposedly one of science's greatest strengths. So, of course, this is something that happens in peer review, or is supposed to happen in peer review. There's supposed to be this sort of deconstruction of the work, this critical eye cast on the work. And sometimes it makes it in peer review, and sometimes peer review fails at that. And so, having an extra sort of post-peer review error correction mechanism is not a bad thing necessarily. And certainly we do have post-peer review or post-publication peer review journals or models that we can turn to. But again, even in those cases, we have a subset of eyes that are looking at this paper, maybe 3, maybe 5, maybe 6. And if we have many more, especially when, the paper goes out into the world and people try to replicate it or they turn to it as sort of some source of authority, it's good to have a way to sort of make sure that we're not kind of relying on something that's error-ridden. Science is so big now, so varied in the forms it takes, so exquisitely differentiated in its roles, that there's no reason why one of its specialized functions shouldn't be dedicated purely to correction. And yet, this whole article bothered the author of this post. And of course, you can see why, because it's like, on the one hand, it's this necessary function. On the other hand, it's framing it in this sort of moralistic and in this sort of moralistic and controversial way. The botheredness started much earlier, so I was very slow in the uptake. So this goes back to a paper that was published in 2005, which was published by a person named John Ioannidis. And so this is where kind of like the roots of a lot of the meta-science comes from. So it comes from this era where there are people who started in social psychology. There are also people in medical research who started to question p-values and why those were important. And there are people, sometimes Bayesian, sometimes not, who question whether p-values are the right way to determine statistical significance. And the problem with that, of course, is that a lot of papers in the literature use p-values, and they rely on p-values for saying whether something is significant or not, and pointing us to things, results that are significant and real versus spurious, and things we don't need to worry about. And so this is a problem, because if there are a lot of papers with this kind of test that's maybe not rigorous enough to really give us a true answer as to what is not spurious, then maybe there are a lot of spurious results in the literature. And so John Ioannidis published this paper in 2005 called Why Most Published Research Findings Are False. So it kind of builds on this idea that if the p-value is lacking, or maybe it's a bad methodology, then maybe a lot of the science that uses that is also bad. Which is, of course, in my opinion, is that's just probably not true. You have a lot of results. The p-value actually does help you distinguish between spurious things, spurious sort of results, and non-spurious results. So this is not. This is kind of, I think, a bridge too far in terms of making a judgment about most scientific findings. Nevertheless, you do get this phenomena called p-hacking, where people will try to get to a significant p-value, and so they might do things like exclude things from their samples, or add subjects to their samples, or design their experiment in such a way that sort of makes their ecological validity less valid. And so they do things that make the experiment, make the p-value significant that don't reflect the real world or don't reflect good practice. So this was a pretty controversial paper, I guess, at the time. And so, this is something that like it catches the eye. It says, "Oh yeah, this is a really interesting question." But the problem is maybe it isn't a question. Maybe it's a question that's made under false pretenses. So something you think about. Even as a brand newish scientist, it seemed fishy, which I've always thought it was kind of like questionable. And as an aside, and I'm not casting any aspersions here, but John Ioannidis also signed the Great Barrington Declaration. So I don't know if that has, there's this connection between the two, but whatever. I was reading a lot of papers about methodology, but this one stood out. In my notebook, I wrote, "This paper is another methodological study, which is modestly summarized by its title. Unfortunately, I don't think this conclusion necessarily follows from the analysis." So the idea is that there's this sort of, you go to the literature, you see what, what papers are using p-values, and there was this whole analysis in the paper, and then it led to this conclusion. And of course, a lot of people found that maybe this was kind of a reach for what you're trying to do. What set it aside, and he's talking about this paper, why most published research findings are false. What set it aside was the sweeping nature of its claim. One of the subheadings is, most research findings are false for most research designs and for most fields. So that's a pretty sweeping generalization. But in any case, and then of course the consequence of this is that you can't really hedge from something like that. Maybe you can hedge from the title, but not from the subtitle, shutting out any possibility that it didn't mean exactly what they said. But for all this, there was very little theoretical input and almost no data to back it up. So they didn't really do this hugely rigorous analysis. So we're just showing in the literature, that the p-value is prevalent, and if the p-value had problems, then maybe the entire scientific enterprise had problems. And of course, that's a pretty large leap, because different fields have different practices with respect to the p-value, and so in some fields you might get prevalent p-hacking, and in some fields you might not. Just as one example. There were lots of papers in that approximate area, but the majority were vastly more measured and importantly brought data to the argument. So there is this set of papers, and there's been this set of papers that have continued to be published on p-hacking and on scientific reliability and on the design of experiments, a lot of things in metascience. And so, there wasn't this sort of controversy around it, or maybe this generated controversy. So, continuing on with this paper, the author, or this blog post, the author kept a summary of some conclusions that went something like this. So this is a long list of conclusions. So the first one is that the peer review process doesn't work. Obviously, if there's a problem with p-values and people are reviewing papers and accepting papers that use the p-value, then peer review is kind of useless. Of course, this also holds true. Maybe you could make that claim from the original example that we gave, where we had people who went and sleuthed into data sets, sleuthed into results from published papers. And if you find errors, then that means that the peer reviewers didn't do their job. So there's this implication that peer review doesn't work. There's also this implication that peer-reviewed papers can have major genre-wide biases. So again, in some fields, you can have different standards for publication than not, depending on the sort of the state of the art of different statistical tests and methodologies. The third is that commonly used tests often reject real effects. So with p-values, like I said, we try to distinguish between things that are the null hypothesis and things that are, other types of effects. And we can't necessarily, with p-values, maybe it's not sensitive enough to real effects. There are these type 1 and type 2 errors that, so we look for type 1 errors, but there's also type 2 error. And it's hard to kind of overcome those in a lot of contexts. Even if papers avoid these problems, most of them are wrong. That seems like a statement that is worthy of just kind of making things up. Pointing out that they are wrong is little or no effect on their citation rates. So we often cite things that are basically wrong. Of course, that's a subjective statement, but there are a lot of papers that get retracted that get citations. And sometimes you even collect citations after they're retracted. But I think what is more likely is that you have situations where a paper becomes a standard in a field, and it's either dated maybe after 20 years, or it's been proven to be wrong by subsequent work, but people still cite those papers. That's a problem, but it's maybe outside the scope of the original paper that we were talking about here, and maybe it has nothing to do with p-values. So put that one aside. If they're not wrong, statistical significance is not the same as actual significance. So again, there is this distinction between statistical significance using, say, like a p-value or some other metric, distinguishing between some real effect and some null hypothesis. But of course, there are things that are significant in the world that are detected by p-values. Maybe the sample size isn't large enough. Maybe the phenomena hasn't been characterized with the right measures, things like that. The next point is important. Insignificant results might be imperceptibly different from significant results. And this again is an artifact of the p-value and how it detects sensitivity, how it detects significant things. And I mean, in science, we're always looking for the significant difference between two groups. So a lot of times if you do an experiment, you have two groups. You have a control, you have a treatment group or something like that. And there's supposed to be this difference that is sort of free from variation. So you should be able to find an effect size that's large enough where the mean of the two groups is different enough with no overlap in their variance to give you something that you can say, this is an effect. This is the effect of this treatment. This is the effect of this difference between the groups. Now, sometimes you don't have enough samples. Sometimes you're not hitting on the right measures. Sometimes it's just a very small effect, and it's hard to pull that effect size out. So it's a small effect size, and it's hard to really distinguish it in an experimental setting. So this is, all kind of saying that there are a lot of problems with the p-value, a lot of things that you can say it doesn't solve, which is maybe not surprising. But does that mean that all the results that are in the scientific, or most of the results in the scientific literature are wrong? I would probably argue against that. Even if you find something really, really, really significant, it can fade away over time, dwindling inexorably in significance. Another point is most papers never get cited anyways, which is not actually true. Most papers actually do get cited at least once. And then this last point, but who cares? The end of the world is more likely than we thought. So I think this comes back full circle to the Great Barrington Declaration. But anyways, I don't want to get into that. I'll just say that there are a lot of problems with this kind of approach to metascience where there's this, is it distinguishable from sort of an attack on the scientific enterprise, or is it calling out errors and trying to earnestly address them? It's hard to say. And when you write papers like this where it's very provocative, it can blur that line. Well, it's easy and important to point out ways in which it doesn't quite work as advertised. It's much harder to say why it works at all, especially given how unreasonably effective it seems to be. So there's this paper, The Unreasonable Effectiveness in Mathematics, which describes why mathematics is sort of a core tool in the scientific and engineering toolbox because it's an unreasonably effective way to get to answers, to approximate things, to find kind of an answer for things that we haven't been able to do. And so the scientific method is the same way. It's very effective at finding sort of mechanisms or finding evidence for mechanistic thinking. And so it's a good, I think, a method that, has flaws, of course, like anything else. Mathematics has flaws, but it works to give you a reasonable answer. So they cite XKCD, of course, as you do, and this is summarizing this reason that the author is interested in. One reason nicely summarized by XKCD, particularly, and I not stress this enough, the alt text, which is here, is that scientists are genuinely curious about the answer to a question. Anyone who's genuinely curious about a question will take these things in and try to do better next time. So one of the things about self-correction in science is that it's personal self-evaluation or self-reevaluation, where you have this, you learn from your experiment. You do an experiment. You might find a significant result. You might find things that don't pan out. And then you try to maybe do another experiment where you reformulate your questions, you reformulate your experimental design, and you try it again. And you keep doing this in an iterative way until you get maybe a very good answer to the question. It's not a one-shot deal where you have to find the perfect answer to a question. They will also ask searching questions about the criticisms. For instance, are most published research findings really false? I mean, really false. Is it a reasonable question about an unreasonable claim? So you ask a question about something that doesn't seem to kind of work, doesn't seem to make sense. And then if you ask enough questions, or if you try to frame your question in the right way, and you really kind of work on that question over time, you can find a way to test that. And you can find a way to really verify that claim. So I guess one thing you see from this article is that sometimes science and like this self-correcting aspect of scientific enterprise is about going and investigating things that have already been published, sort of enforcing and making sure that like good practice was followed, and then the outcome, which is good, reliable science. But there's another kind of route to science reform or science, meta-science, which is question asking. And that kind of backs us up a couple steps to sort of the formulation of experiments and the formulation of how to execute the scientific method. And that is, let's think about claims that are made. Sometimes it's the title of a paper, and sometimes it's about something that people think is true. It's maybe an assumption that we make, and then interrogating that assumption or that provocative thing with a question, not just a question about whether it's true or not, but how do we, kind of make a determinate statement about it. Okay, and then of course, because it's not something that we can always hit on right the first time, we have to keep iterating and kind of improving our question and improving maybe our experimental design or whatever it is that we're doing, our method of investigation, and then eventually we get good answers to those questions. Okay, so going back up to these points here that I summarized, the author continues, such questions fed into the newish field of meta-science, which, having troubles of its own, including the aforementioned thuggishness, has spawned the field of critical meta-science. I suppose calling it meta-science would be silly, but the difference is perhaps a crucial one, which I will come back to later. Some of these studies, or the ideas within them, shorn of any caveats, were eventually taken as signs not that science was self-reflective and self-correcting, but that science was broken or in crisis. So this is where we're getting into this distinction, sort of like where you have a good faith sort of set of complaints about the way science is done and can lead to productive outcomes. And then this idea that science is broken or in crisis, which can lead to bad outcomes. And I think, you can tell the difference by sort of the real world implications. So when you say that science is broken or in crisis, it can be a mode of like kind of self-improvement. Of course, we want to fix things that are broken or we want to solve a crisis. But that kind of viewpoint can be hijacked by bad actors, people who want to, science deniers or other types of people who want to attack the scientific enterprise as a source of authority. And so this is the distinction they're making here. That there are healthy ways to sort of do this sort of self-reflective and self-correcting, or make sure that that mechanism is robust and working. In some cases, it doesn't always happen that way, and so that needs to be, addressed. But there's this other view that science is broken or in crisis that we want to try to avoid. Okay, so this is kind of the shift in some of the meta-science practice that we've seen in this field. The shift in emphasis was used, at least in part, to justify the existence of data thugs and police, and a more direct approach that has given meta-science its particular flavor. So there is this aspect of meta-science where instead of kind of thinking about, just kind of making sure that our process is robust to criticism as well as robust in practice, that we constantly see things as being broken or in crisis. And it gives, of course, meta-scientist jobs or meta-scientist jobs, but it also kind of feeds into this sort of erosion of authority in science. And so this is one of the criticisms of a lot of the meta-science that's the big name meta-science that gets published is that it has this flavor, and because it's this latter aspect of meta-science where it's broken or in crisis is provocative and attracts a lot of attention and a lot of debate, that's maybe a problem in and of itself, because if you have something that really is controversial, you can bring a lot of attention to it, but ultimately it's corrosive. The language is telling. While your peers might politely disagree with your paper, there is at least the notion of equality, collegiality, give and take. They are your peers. The relationship, however, between thug and a scientist is not equal, nor is the relationship between watchdog and watched, enforcer and enforcee. So this idea of being kind of like an enforcer, or there's this term, this idea of good cop, bad cop, where the good cop kind of wants to be your friend, and the bad cop wants to kind of force you to tell the truth. In both cases, they're trying to get to the same goal of sort of interrogating people and getting them to tell the truth, but they approach it in different ways. And so this is kind of the same thing here between the sort of this normal collegiality, this sort of normal peer review, and then this thug approach, which is what the author is kind of obviously against. In the more police-oriented descriptions, we must assume that the relationship is that between police officer and suspect, if not an actual criminal, and it isn't voluntary at all. However, it's phrased, it puts a space between us and them, and linguistically at least keeps the power on one side. If you internally divide science into a group doing science and a group studying and critiquing the methods used by scientists, then you have a system that is in some sense unstable. The binding force that holds science together is relatively weak and depends on the usual scientific give and take. Sure, we all cast a critical eye on our peers' work, but at the same time, they can return the favor, and there's an incentive to understand what in their work is worth building on. If we separate those functions, criticism tends to become an end in itself. Divorced from a positive goal, the incentive shifts towards seeking out subtler and subtler errors, or more trivial and trivial errors, until none is left. So there's this incentive to sort of be hypercritical of a work and kind of like salami slice the errors until you basically critique the entire work and say that all science is false. Sometimes, though, this can also lead to complaining stridently about problems long after they cease to be problematic. So people who will get on their hobby horse about some problem that has been solved and just kind of paint science, the scientific practice, as emblematic of that thing that no longer exists. The difficulty is to keep those aspects of metascience a part of orthoscience, which is a term they kind of come up with, so that they can feed off and exercise one another. The critique needs to go both ways. Certain correctives have been proposed to strengthen science by both metascientists and regular science, and which is, of course, this idea where we need to have open science, where everything is transparent, and we can, see the data and the code and connect this with other articles. And then, of course, there's this other branch of metascience, which is methodological reformation. And methodological reformation is nice, but of course, this runs into a lot of problems with practice and with tradition. So, both of these approaches to metascience requires a certain amount of incentivization, but we want to make sure that incentivization is positive and not negative. This kind of goes on and talks about a little bit about like the trust in science that we need to have in order to have a robust enterprise, sort of the authority of science. And so there are kind of two camps on this. One is that there is this aspect of science denial, and that there are people who want to sort of use maybe the inevitable errors that arise in the scientific enterprise as an excuse to criticize science and say that there are other alternatives that are better and erode the authority of science. And of course, there are other kind of reasons for, sometimes this is maybe leads from actual errors, like papers that have been retracted, and sometimes it just kind of builds upon misunderstandings and other things like that. Yeah. So it's an interesting article. I think it covers a lot of ground, but basically it has this critique of metascience and the two ways to do metascience, and how those kind of feed into larger issues. So those were two selections from this week from the Slack. We have things that come across the Slack all the time, so I probably missed some that were interesting, but thanks to people who posted those. All right, moving on. I want to get into a few articles, and these are two articles that I found from, I guess they're AI-related articles. First one here is something that Paul talked about last week. He pointed out this article on daydreaming and Hope field networks. It's kind of led from the discussion last week, and it was brought up, and I just wanted to go over kind of a quick mention of what this paper was. So the title here is Daydreaming Hope Field Networks and Their Surprising Effectiveness on Correlated Data. These are Hope field networks. This is a physics-inspired neural network. As such, it's basically operating like a spin glass model, if you're familiar with spin glass models in physics. So the abstract reads, to improve the storage capacity of the Hope field model, we develop a version of the dreaming algorithm that perpetually reinforces the patterns to be stored. So this is sort of the Hebs rule applied to learning in this model. So we have a dreaming algorithm that perpetually reinforces the patterns to be stored. Of course, we talked about Hebbian learning, which is where you have this association between two things, and that strengthens a connection between those two things. We perpetually reinforce the patterns to be stored and erase spurious memories. So it's important to do two things when learning, of course. You need to be able to reinforce patterns that occur again and again, and then you need to be able to erase spurious memories or spurious patterns. So you don't want to store the spurious patterns, but you want to reinforce and store the meaningful patterns. That's basically what's happening. For this reason, we call this approach daydreaming. So the idea is that we're dreaming, and this goes back to a neuroscience finding, which is trying to figure out the function of sleep in organisms. So we sleep, and we have different levels of sleep and all that, but one of the functions of sleep is, of course, to regenerate, to go into a resting state. But another purpose, specific to the brain, is to encode learning. So they encode that day's learning. So you learn things during the day, you experience things during the day, and then at night you consolidate those memories, replaying those experiences in your head. So, if you travel a certain route to work or to school, you review that route in your head as you sleep, and then that route gets consolidated so that you can retrieve that from long-term memory, and eventually you learn your route, and it becomes automatic. So, the first day you do this, you might have to look this up on a map, and you have the experience of traveling to that place, and you might have to do that for a couple days, and you're kind of replaying that in your head, and you're consolidating that memory until it becomes a stable long-term memory that you can then draw from. They propose this model called daydreaming for the Hope field model. Daydreaming is not destructive, and it converges asymptotically to stationary retrieval maps. When trained on random uncorrelated examples, the model shows optimal performance in terms of the size of the basins of attraction of stored examples and the quality of reconstruction. So there are two things that are of interest here. The first is, when I say stable memory, I mean a memory that doesn't vary or doesn't show a lot of variability. Because if you encode a memory that is basically true on the outlines but isn't stable in how it can be retrieved, or if it's not stable in terms of its details, then it's not necessarily a good, it's maybe it's spurious, or it doesn't really help you too much. So what they're looking at here are the basins of attraction. So when you have a basin of attraction, it means you have this stable thing where the system always gravitates towards. So this tells us something about the stability of that memory. And then, of course, the quality of reconstruction is another parameter we can use to look at, how accurate that memory is. We also train the daydreaming algorithm on correlated data obtained via the random features model and argue that it spontaneously exploits the correlations, thus increasing even further the storage capacity and the size of the basins of attraction. Moreover, the daydreaming algorithm is also able to stabilize the features hidden in the data. Finally, we test daydreaming on the MNIST dataset and show that it still works surprisingly well, producing attractors that are close to unseen examples in class prototypes. Okay, so they define the Hope field network in terms of its mathematics here, and defining the network itself in terms of n neurons that take on discrete values, and p discrete patterns are the memory stored in the network. And then the retrieval of the memory is successful if the spin dynamics converge to one of the stored patterns. Okay, so that's how they define that. And so in terms of why they call it the daydreaming algorithm, since we stress that daydreaming can be iterated indefinitely, here we review the literature on alternative learning rules, arguing that rules that avoided the pitfall of dreaming too much showed other undesirable properties, the most common ones being the addition of non-local terms and the vanishing basins of attraction. So the amount of dreaming that the model does is important. If it does too much dreaming, it can undermine the positive attributes of sort of selective dreaming that they show in this paper. So it's important to have, to let the network explore the space in the right amount. So I think that's enough for that paper. And this just shows the daydreaming learning algorithm in terms of the pseudocode. So it's showing that there's this initialization with the Heb rule. Then, you implement this in epochs. You have n steps in each epoch. You pick an example at random. You initialize spins at random for the spin glass model. Then you run the spin update dynamics, you update the coupling matrix, and then you normalize after each epoch. So you have this sort of dynamical system that governs the evolution of this network. You go through each epoch, you define the number of steps, and then you normalize after each epoch. And then this just shows that the daydreaming algorithm has good asymptotic behavior, means it converges, and this shows how this learning process works. So that was follow-up from last week, just to talk about the daydreaming paper. This paper here is from the archive, and this is a cognitive science flavored paper. But does talk about AI and kind of this transition between the AI that was pre-deep learning and the AI that we have now, which is based on deep learning. And thinking about symbols and symbolic representations. So we talked last week about neurosymbolic models, and the daydreaming was actually sort of in that direction of neurosymbolic learning. And there's another paper we talked about by Josh Tenenbaum that's a good example of neurosymbolic learning. In this case, we're talking about sort of one distinction. Okay, so one distinction between the pre-deep learning era and the modern era is that it's sort of the triumph of data over symbolic learning. In other words, we used to use symbolic learning back when we used chess as the metaphor, and we were able to represent things in terms of this table of looking up symbols to represent things. And that was thought to be the future until data-driven AI really kind of produced a lot of good results. And like a lot of things, when you point in a certain direction, you kind of go in that direction, you forget about what's in, the other back in the past, or what might be useful from other directions that you can incorporate. So basically, symbols have kind of fallen into disfavor, fallen into disrepute. So the title of this paper is "Wither Symbols in the Era of Advanced Neural Networks?" Which means when we're doing deep learning, what is the role of symbols, if any? So this is definitely it's from this machine learning community, but it's also squarely from the cognitive science community. So the abstract reads, some of the strongest evidence that human minds should be thought about in terms of symbolic systems has been the way they combine ideas, produce novelty, and learn quickly. So, one of the things about symbolic AI is that it used the human metaphor. In other words, since symbols are important to humans, that symbol should be sort of the model for simulating or making an artificial intelligence. And of course, you can do a lot of things with symbolic systems, but they have their drawbacks. And so, we still, especially in cognitive science, we want to think about intelligence and about minds as being symbolic systems. We argue that modern neural networks and the artificial intelligence systems built upon them exhibit similar abilities. So we don't want to throw out the symbolic baby with the symbolic bathwater, I guess is the lesson here. We have reasons for thinking that intelligent behavior or minds involves symbolic systems. And so, we can learn a lot from training models on data, as much data as possible, but we have no symbolic basis for anything else. So we can find a lot of patterns, but we might not be able to distinguish between spurious patterns and real patterns without the symbolic layer. So this undermines the argument that the cognitive processes and representations used by human minds are symbolic, although the fact that these neural networks are typically trained on data generated by symbolic systems illustrate that such systems play an important role in characterizing the abstract problems that human minds have to solve. This argument leads us to offer a new agenda for research on the symbolic basis of human thought. So basically, okay, so let me go through this argument once more. So we basically want to make this analogy between modern neural networks and sort of human minds, and those exhibit similar abilities. This actually works against this argument that cognitive processes and representations are symbolic because we use this data-driven approach. If we can get maybe, human-like results with neural networks that are driven by data, then the mind must be similar to that. But of course, it undermines a lot of what we've learned from cognitive science, which is that human minds are essentially symbolic. And this is, of course, also undercut by the fact that neural networks are trained on data generated by symbolic systems. So there's this interplay between symbolic systems and non-symbolic systems, or the sort of data-driven approach to training models and getting them to behave like human minds or something similar. That is an open question, basically. There's this question about whether artificial neural networks can represent symbolic systems, such as logic and grammar. And this has gone back, this argument has gone on for as long as neural networks have been around. So there's certain properties of symbolic systems that we can bring to bear. And there are also properties of these data-driven systems that play a role in this debate. So properties of symbolic systems, and the two that they highlight in this paper are productivity and compositionality, have been proposed as central to human intelligence. So when we have neural networks that cannot demonstrate these properties, it's a problem for neural networks being sort of this analogy to human minds and human pattern recognition and whatnot. Moreover, probabilistic models that operate over logic, grammars, or programs have highlighted how symbolic systems can be used to characterize the inductive biases that allow people to learn from limited data. In this article, we revisit these questions in light of recent advances in AI. Training larger neural networks with more data, using new architectures and training techniques, have resulted in improvements in reasoning, learning, and using language. So for instance, large language models based on the transformer architecture display impressive productivity, and the training technique of meta-learning results in greater compositionality and rapid learning. So it's not that you can't do these things you can't achieve these sort of symbolic properties with neural networks. It's just that there are, certain methods that can do this to an extent. But we still have this sort of argument. Maybe it's a little bit artificial, but it's definitely, something that cognitive science can maybe address. We argue that these advances undermine historical arguments that human minds use symbolic systems in a way neural networks do not. So this is this sort of issue of how artificial systems miss what cognitive systems and biological systems produce. It's sometimes hard to pinpoint what that missing stuff is, but it's definitely there, at least qualitatively we can tell. And so maybe that's, maybe that's not true, but there is this intuitive sense that that's the case. And so we can address this gap between artificial systems and the mind in terms of maybe, focusing on symbolic systems. Neural networks display comparable compositionality, productivity, and inductive biases to humans when evaluated against the same empirical standards as humans. Therefore, further progress in understanding the similarities and differences between human cognition and neural networks will require new methods for evaluating such claims. So maybe it's not a matter of neural networks not being able to do these things that symbolic systems do, but rather we need new tests and new ways to understand, that difference. So recent advances also suggest a way to resolve this classic debate by levels of analysis, and we'll get to the figure 1 pretty soon, but I wanted to go over this preamble. These demonstrations of compositionality, productivity, and rapid learning arise in neural networks that have been trained on data generated by symbolic systems. Similarly, symbolic systems also feature strongly in human experience, both within and across lifespans. Thus, for both humans and machines, symbolic systems are useful in characterizing the abstract computational problems that need to be solved. And this is what Marr called the computational level. So the computational level that Marr proposes, and Marr has these 3 levels, involves symbolic systems as well as sort of this computational aspect. The subsymbolic processes and representations that implement these computations in neural networks play a complementary role at Marr's algorithmic level, which is a different level, and capture other behaviors that defy easy symbolic description. Okay, so they kind of walk through this, and so this last sentence here, evaluating this hypothesis will require a new research agenda with 4 interrelated threads. The first is designing more diagnostic tasks for probing symbolic representations. So if we want to sort of get into maybe the potential symbolic representations produced by a neural network, or the significance of symbolic representations in human cognition, we need better diagnostic tasks for this. The second is developing a deeper mechanistic understanding of neural networks. So what are neural networks actually doing? We've talked about some of that with credit assignment and with other things that we do to look at what neural networks are producing. We don't want it to be a black box, just as much as we don't want the brain to be a black box of the mind. Then the third is training neural networks in a more developmentally plausible way. So this goes back to this developmental aspect. And this is a very popular thing to talk about now. But we want to be able to figure out, because we know that human cognition comes from development, how can we train models in ways that mimic development, in ways that mimic the acquisition of symbols, in ways that mimic the acquisition of, say, like language. Language isn't just something that, we'll take humans as an example, something that humans are presented with a list of words, a list of grammar, and then they have to construct it kind of at random. Language is learned in a deeply embodied manner. Language is learned kind of through trial and error. And, there are ways that language is acquired through development that are reflected in the way that models are trained. And probably that has something, we always make this assumption, of course, that when humans do something, it's for a reason. So this is likely to be important for acquisition. Although, it may not be necessarily important for acquisition. It may just simply be the way we acquire this. And if we're talking about, an artificial system, it might be just as easy to throw a list of very giant list of things up. In any case, that's something we need to explore more of. And then finally, creating more explicitly cognitive neural networks that explain human mental processes. And this is taking us back to connectionism, and sort of like we talked about last time, we had this sort of splitting connectionism between the connectionism that happened before the deep learning revolution and then the connectionism that's happened since. And so these more cognitive neural networks kind of call back to that pre-deep learning connectionism aspect where, we want to use neural networks maybe more as sort of like an experimental verification test bed instead of as this data-driven applied model. In any case, they make these sort of recommendations for a new research agenda, and it's basically bringing cognitive science into AI more explicit. This is figure 1. This talks about the signatures of symbol processing in modern neural networks. So we have these 3 things here: compositionality, productivity, and inductive biases. So compositionality, which is the first one here, refers to the ability to flexibly construct thoughts out of a set of simpler elements. So this has a linguistics relevance to modern linguistics, and that this is the way we think about linguistic acquisition. It's through compositionality. So we learn a bunch of words, and we can apply those words to objects, but we have to compose different words into concepts. So for example, if we have a teddy bear, we know what a teddy bear looks like, we know what the object looks like, and we can attach that word. We also know what a skateboard looks like, and we can attach that word. And then we know what Times Square looks like, and we can attach that word. But by themselves, that's fine. But then when we want to compose something, we have to be able to add together these 3 words, and then add together the objects in a way that results in what we see in D, which is this image of a teddy bear on a skateboard in Times Square. And if we wanted to describe this linguistically, we have to put in intermediate words. So, if we wanted to describe the scene, we'd have to say, there's a teddy bear on a skateboard rolling through Times Square. And then, another person who hears that could evoke a mental imagery that maybe resembles this image. And so but the important thing here is that there's this compositionality. And this is something in artificial models that is, not automatic. So an artificial model will automatically make this connection. It won't be able to build an image like this in a descriptive manner and link it to the language in this way. So that's what compositionality is. And again, there is this sort of aspect of being able to put together concepts and being able to link it with images. That's really interesting. And it's interesting to cognitive scientists, especially linguists, but also interesting to how machines can generate concepts and other things like that. So the next one is productivity. And so productivity in B refers to the ability to extend observed processes to new examples, generating a potentially unboundedly large number of novel thoughts or sentences. So if we, again, and this is not compositionality, but it's another way to sort of generate new things from the original things that have been acquired. So we might have a training data set that includes the terms tropical and Brazil. And we want the model to generate things from these two terms, associate these two terms, and generate things that are similar to those two terms. So when we train our data on these two words, or training set that includes these two words, tropical and Brazil, the model generates words that include non-Neotropical and Brazilianisms. So it's going to generate a lot of things that are maybe not so relevant, but it'll generate things that are relevant to that association. And so we end up with what we see in E, which is this graph, which shows n-gram size versus the proportion of n-grams that are novel. And this is, of course, an evaluation of linguistic data. And it shows the performance between humans in red and the performance of GPT-2 or a large language model in blue. So we see that there's this sort of correspondence between humans and GPT-2, except at large n-gram sizes and points where the proportion of n-grams that are novel increases. So we have this S-curve for both cases, but GPT-2, I guess, outperforms humans at this very large area, but underperforms humans in this intermediate area, which would represent most natural language. So again, this is a distinction between artificial models and human cognition. And then finally, we have inductive biases, which is this stated by the statement here. And inductive biases refer to the set of assumptions that guide how a learner learns from training data. So this is where we have this graph F, which is evidence for symbolic inductive biases in neural networks. With a training approach based on meta-learning, a neural network can learn symbolic formal languages from small numbers of examples. So we want to be able to, we don't want to have to train our model incessantly. We certainly don't do that with humans. One of the benefits of human cognition is that we can have a relatively small number of samples and do a pretty good job of generalizing from it. We can also learn what symbols mean with very little data. So this is an example here of the difference between a basic network and a meta-learning approach. And so this is a graph here in F. This is the number of training examples up to 10,000 versus at the F score for learning formal languages. And we can see that there's this difference between a basic network and a meta-learn network, meaning that we have to use meta-learning as a strategy to improve performance at low numbers of training examples. And then when we get up to 10,000, the basic network and the meta-learn network converge. So when I talk about meta-learn networks, I'm referring to things that are cognitive-like in nature. So we have the strategy that mimics cognition and gives us this ability to sort of do meta-learning. So again, for like large numbers of training examples, basic neural networks don't do as well as this sort of cognitive strategy. Okay. So I'm not going to go through the rest of the paper. I think that's, I just wanted to set up this argument and kind of make you aware of this paper and kind of what people are thinking about in terms of cognitive science and how to apply that to modern AI. Looks like Jesse's here and Morgan's settled in his location. I don't know if you wanted to make any comments or if we wanted to do any kind of updates or what.
I got a lot to catch up on. So I wanted to first say, what is it? All research findings are false.
Yeah.
was like the original. I don't know if it's the original clickbait,
Yeah.
but damn close, right?
Yeah, yeah.
Yeah. I love the. Well, we didn't really mean that. Yeah. But sorry, your point though with that. I'm just trying to remember some of the comments that you had around it. In the what was the context of that paper?
So the context was that there's this aspect of meta science that is sort of, I mean, it's kind of grown into this sort of malignant force. And yeah, so like there is this argument on social media, and this is missing context, but that people feel like there's this sort of authoritarian nature to meta science where people are trying to enforce things and they view the practice of science itself as inherently flawed. Whereas, maybe the better way to do it is to say, well, if we have better checks, say through peer review, or if we have better sort of internal practice and incentivizing people to do that, then that's a better approach.
Yeah. Well, as well as the problem, certainly some of the thoughts that I had when you were covering that, especially around the problem of citations that continue getting citations after they've been retracted. And in a sense, it reflects the decentralized nature of science, right? In that there isn't actually some boards deciding what we all think, right? And so there is that. So not everybody gets the memo,
right?
But it's not 100% a bad thing. It just and certainly there's been it's really helpful to cover what's her name, is it Elizabeth Bick?
Yeah
is the woman, so the woman who started Retraction Watch, or
well, I think she does the thing where she looks at different biological papers and looks at the images to make sure they're not.
I mean, that's how she started,
Yeah.
And she quite rightfully says like I was doing bare minimum checking.
Right.
Like I just is it the same image but flipped?
Right.
Partially just to shame the journals in terms of like you could be doing this too.
Yeah.
Yeah, and how much this is reflective of kind of pay to publish, and the incentives being wrong in the journals, in in the academic institutions, demanding papers regardless of, again, quality or impact or things like that, or again, there are metrics, but again, there are metrics that start to be gamed, right? And which again I think is is something that you see a lot with with large language models.
Oh yeah.
Anyway, but big problem that that is only going to be worse as we have more algorithmic ways of producing content.
Yeah.
So and then sorry, I had to drop off from 8 to 8:30 because we're starting Connection, which is a program. It's a kind of 4-week boot camp for neuroimaging training in underserved, under-resourced locations. Okay. So it's predominantly in Africa, or at least the two physical sites are in Nigeria and Kenya. So we'll be looking at some of the issues around getting things running on the cloud too, and Neurodesk running on compute services like IBM Cloud. Just to, but covering neuroimaging. I'm on the microstructural team for that, and it was a good workshop for 3D bioprinting. We're moving forward here on that. I'm trying to think of updates. There's a lot of lab infrastructure. Getting old biotech equipment and trying to figure out how to get software to work it.
Yeah.
And how industry is has locked down some of these devices. So thinking about what the next devices we're going to be looking at in terms of the 3D bioprinters are very expensive commercially.
Yeah,
you can do some remarkable things converting consumer printers. I don't know whether anyway, looking at the open flexure microscope, and I think microscopy is one of those absolutely key areas where, again, I don't know if we can approach something that's more like that can come close to kind of confocal microscopy.
Yeah.
With at a like an order of magnitude less kind of I'm sure somebody would have done that.
Yeah.
Like there's enough need, right? So, but I'm looking forward to learning what the problem is. Like what's the crucial component that makes it so hard. Other than that, next week is getting kids back into school.
Oh yeah. Yeah, that's always a challenge. Jesse, how are you doing?
I'm okay. How are you?
Good.
I'm not sure what to comment on at this point, and I know I missed a whole bunch earlier as well. I will loosely promote an event, I guess, that I hope to be attending at next week about this time. I don't know if it was mentioned earlier, but I think Morgan will be there at the ArgLab Summit. It's here in MIT Media Lab. It's hosted by the Augmentation Lab proper, but also like some of the Ecolopto stuff there. Eddie from Ecolopto does stuff with ArgLab. But it should be a very interesting event in terms of bringing a lot of people. There's like artists and technology and startups and whatnot too. I'm still sorting out some of my a lot of stuff here. This is a side comment. The event will be great. I'm looking forward to it. Side comment and just sort of food for thought that I'm dealing with at large is it seems very much easier, and this maybe even ties to the meta science discussion where I came in on at the end. It seems very much easier to get people excited to do hackathons about technologies or events, like very discrete build a tool, build a product. And I'm quite curious because I think I want to start. I want to make an event at some point. Maybe even it would be over 18 months out, but maybe 12 months from now would be awesome. But I'd like to make an event that really centered some of the stuff that we've talked about too. Maybe not necessarily in theory as much as in practice, but around making a conference that's synthetic in its outcomes, around incentivizing people to do things that aren't just these discrete I don't know, innovations, but something a bit more coordinated or wider ranging. And I know that's much harder to do. Like, I understand there's reasons why that's not quite as appealing or maybe seen as tenable. But what I'd really like to do is make a serious effort of, not, we've talked about, like, I've used phrases like doing science differently. But also sort of, I want that to be connected to larger questions, or larger problem spaces too. Like that, I don't want it just to do scientifically. I imagine. I don't know if any of you all remember the old Envision conference series, which was held at Princeton for a while. I happened to find those T-shirts from that event again, and it's unrelated to my want to make an event eventually. But that event was really wonderful at the time because it was the first event I'd really been exposed to. It was open to undergraduate folks, and open to younger people and early career people. That was accessible and somewhat local and funded enough to make things, appealing for people. But put a lot of, it was hopeful about the future, but it really put a lot of the cards on the table in an undifferentiated way and say, okay, let's bring all of these voices into the room, from like Ruha Benjamin. That's where I learned about Ruha Benjamin, for example. And she's a critical, progressive voice in the space of technology and future studies and race and identity and all these other things going on, right? But that, like, Joanna Bryson was at the same conference. Emil Torres was at the conference. Logan Thrasher Collins was at the conference. Like, it was just a great, what it attracted and brought together was fantastic. And also, like, Avery and myself, from that have been in the lab were there. And it's inspiring because of the breadth of it and the scope. And I think, okay, that was 7-8 years ago for some of those things. And now, the world's a bit different. And I think in the middle of the 2010s, you would have a particular, I don't want to say optimism, but what you're asking people to seriously think about the future and doing things differently and getting involved, I think is just a slightly different flavor now, given how the world has changed since then. So I don't know. My open thoughts for today are along these lines of, if a conference was to be made, or some kind of an event was to be made that incorporated a lot of the things that we've talked about here, and obviously, I think maybe even a centerpiece for what I want to do is things that are related to sort of frontier map, and the concepts of, like, how do you identify these trajectories, and then also the practical versions of how do you lead people or foster groups doing research, groups trying to do the investigative work, like the kind of project management stuff that we talked about, many professional development things we've been talking about. Sort of a more, I don't want to say, realistic, because I don't think that's really a fair word, but this balance between, it's much more fun, it's much more attractive, I think, to just be sort of blue skies hackathon, let's make cool products and technology. Like, I get that. Like, that's you're not to present these things as shady used car salesman vibes by any means, but you're being able to sell. All right, let's come here. Have a great 24-hour period. We're gonna focus this to be people, like-minded people. We're working and come away. We walk away, and it's great. And we're done. You can go viral because of our coverage of the event, and you have your new thing, and now you can pitch it. Like, great, that's all fine. But I would love to make something that's even like I attended. I'll this for example. I attended the public AI work summit this week. I mentioned it yesterday. I could only actually was trying to go to the workshops, but I don't know if I got waitlisted, even though I applied earlier or whatever. So I was disappointed to go to the workshops. But the first day was just 3 or 4 keynotes. And it was very nice. It's good stuff. But one, I want to make events just like that. And I think some of the things that we talk about would fit well there. Things I'm doing with Joe will fit well there, and I think we could all have, we could do a discussion. We easily could do some kind of a, project management, professional development for open source or alternative AI education, whatever. So we could do the exact same thing. We could have a 1 to 3 hour keynote day and then a 1 to 2 hour workshop day. Like we do that next week. I'm not saying I can't do it next week, but because I'm not using these things as negative examples, as like, oh, these are bad, but more, I'm really starting to think, and I'll probably bring this up slowly over time. I want to make a different type of event, a little like further out, and particularly I do want to do something around this time next year because I know I anticipate the chaos of the year that unfold. So I'd like to have something in the works for that in particular. Ideally, that can be sustainable enough for go through that period. But I don't know. I've recently shifted from thinking, oh, this is an event. This like what a weird set of things to put together. To now, it's like I think I'm taking it more seriously, and I'm curious. Even understanding the sort of trajectory that initially I don't think I'm going to be able to do one event that's just totally going to incorporate all the changes that I'd want to see. I don't think I have the clout or pull or means to pull it off. But sort of like in the Quentin Tarantino tradition of making the same film every time you do it because you want to refine the product so much. Which I never understood, by the way, kind of agitated me, but now I kind of get it more.
Yeah.
That I'm trying to build more things. Like I get it why, even though it was sort of Anyway, I could see how this could be made a bit more piecemeal. So that's my contribution for today. It's all big future wonderings and talks and planning, but I am tightening up something to Joe. I am making another organization to do some very different things. But in the future, I'm starting to put out feelers to see people who would want to do some of the stuff that I've been mentioning here. There's enough to get started with, so I'll leave it at that for now.
Okay, that sounds great. Yeah, so yeah, I've thought about hackathons in my career, and like we talked about them in this group, and I've talked about them in other contexts. And there's definitely an art of getting together a successful hackathon. You have to have the right mix of people. You have to have the right topic. You have to think about it not in terms of kind of just letting people work on their own, but also not, kind of micromanaging everything. So it's really kind of, you want people to be creative. That's the whole point of a hackathon. But you also don't want to just leave them to their own devices, because that never really works. It always has this sort of intermediate, there's this intermediate recipe to a successful hackathon. Some of that, of course, is technological, and some of that is conceptual, right? So it's always kind of hard to pull off and hard to get the right mix.
Yeah, I watch me say this and then go make a hackathon. I really don't want to make a typical hackathon.
Yeah.
Like, and it's tough because what I think when you say hackathon, to continue to just double back and contradict myself repeatedly here, I think it's great because the expectations are so clear. Like when I think hackathon, I know exactly what to expect. I know what it is. I know what the thing is. I get you have a very clear structure and idea about what's going on, and I think that's great. And when you have a summit or whatever you want to call 2-day conference, 1-day conference, like you could, and all the stuff with Nickwick too. Like I think comparatively, or to use Nickwick as an example, which is New York Celebration of Computing, shout out to them. I think Nickwick has been fantastic at meeting its goal, its target audience, its needs, and even see like dealing with funding and choices. I really, Nickwick has been so great to be a part of and see how their mission and what the event they made to do it works. And I think it's it's sustainable. It's not too much of a risk. Well, it's a risk, but it's not too much of a. They're staying in their lane the right amount and moving forward the right amount. And I was like, okay, that's cool to see. And so it's like using you have Nickwick, you have hackathon models, there's sort of this. Here in Boston, there's this. I think it's similar to Boston or New York or the Bay Area and so on. And I admit I'm much less familiar with the West Coast, but there's sort of the frequency and opportunity of certain events is just very different. Like, and that was a big reason why I came here from Albany, was because it would just be so much. It was like you'd have to drive so far just to get some regularly happening things. And now if you're in the space, to do it, it's very different, the dynamics of what the environment holds in person. That's even for in-person stuff. Where I'm going with this, I guess, is it's going to be an interesting thing, and I appreciate being able to talk about it here with you all. Just as you know, but just to say that it's sort of this choice to be made about when and where do you want to push things forward or more alignment with the mission or vision that you want to have. Because it's be much easier to do a hackathon, a summit type thing that's just discrete, just to get the community up. Because that's the thing. Like, I don't. Maybe to Bradley's point, like I don't think I could just pull off what I want to do yet without a lot of. I'd have to really work to build up a certain community of it. But at the same time, certain things are definitely tenable right now to do. So it's going to be some strategic choices about, what can be done shorter term, and how seriously and how ambitious do I want longer term, fuller versions of what I want to see happen emerge. So I don't know. I'll leave it at that. But I appreciate the discussion, and I mentioned this a bit in the Slack, but more about this ahead.
Yeah.
And specifically the more tenable versions of things. Like I said, discussion series, whatever. But yeah, like I don't know. I don't know what you all would be up for. Maybe it's something that in the most immediate sense, next week, when Morgan's in town and we're all here, we can have maybe a very brief, I don't know, all discussion about some potential things to do on these fronts in like basically the rest of this year, because there'll be opportunities to do things this year.
Yeah.
I think I personally see an area where it's like stepping up into someone who's hosting or running events might be an avenue that I go down a bit more. Even like virtual, simple online events. That's all. We move on.
Okay. Yeah, no, I like that. And I don't know, I don't remember if I've ever presented on I have a unit in my project management course where I talk about hackathons in this larger category of public meetings and athons and things like that. So you can have like hackathons, docathons, ideathons, whatever. And then they build upon this larger model of public meetings where you have discussion groups, you have meetings, just ways to organize a project, organize a community. And that's kind of, exploring that sort of larger space of options. So like the hackathon is typically kind of focused on certain expectations, right? You expect to produce something useful at the end, or sometimes it's experiential. And then like but that's a public meeting. It's a type of public meeting where you want to bring people together. You have an agenda. Maybe you want to do accomplish something. And so I think thinking broadly about that category of hackathon, with all the baggage that it has in tech and all that, I think it's interesting for what you want to do, because it's like rethinking. I guess what you want to do is rethink like the conference or the mini conference or whatever. And so I think thinking about it in terms of, okay, what is a hackathon trying to do? What is a mini conference trying to do? What do I want to do? And how do we get all that out into a really good event? I think that's the way to go.
Yeah.
Yeah.
Yeah, exactly. And I think it's a little bit of, it's the mix between the broader, bigger ambitions and sort of making some of these breadcrumbs to lead there, for sure. So much. Another thing, a very brief shout out to the data and direction crew. I don't think they've ever really been able to make it to this meeting. It's mostly been distributed. Everybody's kind of doing their own stuff, but I'm very heartened by what they're doing. This is a super brief update. We have someone who is basically learning NLP for the first time, a computer engineering background, but learning NLP and learning how to basically just do some really simple NLP to sort of break down ethics policies and understand what's in them, which is a very good starting point for things. I have someone looking at AI inequality in education and the pressure for different schools, like K through 12 schools, to adopt technology that they can't even administer or don't understand. Is one extreme case, and how certain different like socioeconomic status schools, like being AI or screen free, is presented more as this luxury. You don't have to, you have time away from this too. Whereas, that's just one angle, but there's this massive disparity along, save money by having more AI and customized tutoring and manage these 500 Chromebooks, and you're trying to make a person an IT administrator and a teacher. And so just the disparities that are happening there, no less the actual implications on like GTP and learning and all the controversies in that space too. But having someone look at that's really interesting. And then a couple other things going on as well. I never sent that one Medium thing to Medium because one of the interns, Mello, was at the FACT conference, and I need to send that too. orthogonal medium. But she was cool that she was at that event. It's the big fairness accountability one in Greece this year.
Okay.
So yeah, it's been really cool to see what they're doing, and I think if anything, it's been very heartening to see. To go back to the conference thing momentarily, seeing people, seeing the process of going through basically a very specific call for involvement for this project. It won't be a huge project. It won't be a huge for the more tailored the focus for what I really want it to be, the less widely appealing it will be, because that's the nature of things. So I'm figuring that out, but it is heartening to see for a small scale internship like data indirection right now. It's very heartening to see what people are doing there. So shout out to the data indirection cohort so far.
Well, that's great. Thank you. Yeah, thank you for the update. And it'd be great if some of them could attend some of our meetings. I'd like to get like kind of to know a little bit more about what they're doing, and definitely push that post to the medium, because that would be great to see some updates on what they're doing. It sounds like you're really kind of hitting some pretty good activities at this group.
I don't think I'll do this. It was one of those things where I don't think I'll structure it the same way again. But I'm fortunate that the people that it worked out for has done. It's basically 3 totally different internships. Like it's not we're working on the Diva Worm or sustainability. It's basically customized and a mix between like mentor and advising and this thing. But I'm okay with that. Like for this term or for this cohort, for this group of people, I'm okay with that. But at the same, I should say this too. I forgot. Like not only the I haven't gotten feedback from this yet entirely, but the education piece right now is sort of just a series of, you could say, blog posts. But what I actually am considering doing with it, if the person wants to go there, is doing a more formal like white paper report on this space, because the person is very talented academically and knows how to write. Like they're fine with writing, but they specifically wanted to make some outputs for everyday folks, like very science communication that's not as accessible. But I'm like, geez, we're finding the citations, we're doing the stuff, they can do the writings, and why don't we just? It would almost be like double dipping already, because we're doing the rigorous part of it. So that's something I would that just came up this week, and I kind of I'll ask you more about that offline on Slack, your opinions on that. But I would like them to be here, or at least have some things that are more interactive, and get your feedback and the lab's feedback on too. So absolutely.
Okay. Yeah, that's worth mentioning also that this fall, for fall term, I'm going to be doing the Illinois Model Builder again. I did this last fall, and I'm going to do it this fall. And this is the sort of experiential course like you have, where you have a small cohort, and they're all going to be working on projects, and we have these topical lectures every week. And so, and I want to apply this to like different schools. So like this is Illinois Model Builder. I'd like to have other schools where I do Model Builder, and it's a little bit different in each case. But
is there a way that I could I guess like course website, or just a way that I could convey to somebody else who doesn't know at all what Model Builder is?
Yeah, I'm going to be I am putting up a website right now that's going to kind of cover it. I used to have it like kind of in the private, content distribution system for the university, but now I'm going to put it on a website. So I'm getting that website ready, and I'll put it up. It's going to be, I'll put the public facing link when I have it done. Okay, yeah.
Let's follow up on that later and everything else too.
Yeah, so yeah, that's great. So yeah, thanks for the update, Jesse. Great. So I wanted to mention one more thing before we go. This is the last I'm not going to get into this, but there was one more thing I wanted to talk about, which is this article in Science. This is by Melanie Mitchell. This is sort of an opinion piece, expert voices thing, and it says why AI chatbots lie to us. And so it's kind of going over why AI chatbots make stuff up and fabricate things, and how, you know, their misaligned behaviors that they exhibit. And I'm not going to get into that this week, but I just wanted to mention it as a thing that exists in the world. And we might get into this more next week, but I think that's very relevant to a lot of things we've been talking about with AI models, and of course, some of the critiques of them. So, okay, so that's the last thing I want to talk about. So, yeah, I don't think we have anything else. Do we have anything else we want to say before we go, or anything to mention before we go?
No, I might try to flesh out some more things for next week's both the Google Summer Code and the Say Here. Well, I mean, next Saturday would be the summit, so maybe we can try to do some kind of a check-in or live from ArgLab Summit. It's Orthogonal Lab Saturday morning.
Yeah, that would be good. I'd definitely like to do that.
I'll try to figure out the timing of the event. I don't quite know yet. We can do that, and then Friday, I'm gonna aim to fit. I have the presentation, for the technical presentation thing. So maybe I can try to do that Friday or something else Friday. I feel like I'm due some to deliver some things there. So that's my aim for next week.
Okay. Yeah, that sounds great.
All right. See you all later.
All right. Thank you for attending.
Yep.
See you next week.
Take care.
Bye. See you next week.
Take care. Bye.